I can do this anywhere in the country. I can turn on a tap and the water runs out. We take it entirely for granted. I can do it at any time of the year, day or night. The people here in Chester use some 6 million gallons of water every day, water that comes from the River Dee. How is it possible to make sure that this water is always available and always safe to drink? Well, the answer lies some 60 miles away at Lake Bala. Lake Bala, or Llyn Tegid. But of course it's the rain which is the source of all this water. Some 3/4 of Britain's rainfall falls over upland regions like this in North Wales, feeding the tributaries of the River Dee. So how can we make the best use of this rain? What we want to do is to catch it and store it in a reservoir. And we can either do this by building a dam across a valley with a lot of complex pipe networks, or we can do what they do here, which is to use a natural lake and the River Dee, which is the natural river flowing out of it, as both the storage reservoir and the pipe network conducting water downstream. A natural lake, feeding a natural river, but supplying man's needs. It's this interaction between man and nature that we're going to show you, for that's what the deregulation scheme is all about. The key to the scheme is the level of the lake here at Bala, and how the level is monitored and maintained is crucial. This is the River Dee downstream of the lake. To fully understand the Dee scheme, we've got to know a bit more about the river and its uses. People use rivers, both as a resource and for pleasure. It's used for farming, by industry, and by the community as a whole. This aqueduct carries the Shropshire Union Canal. That's also fed by the river from a pumping station just below. Not only do we take water from the river, we also dump waste into it. This sewage works is just one of many which releases effluent into the River Dee. And after all these inputs and outputs, 75 meandering miles and 2 days later, the river finally reaches Chester.
This is a model of the Dee catchment area, showing what it was like before we made huge demands on the water. Here is Lake Bala, with the river flowing downstream through the Dee Valley and on into the city of Chester. At this point, the river flows over Chester Weir to meet the tidal waters of the Dee estuary. Now, the Dee is a regulated river. What does that mean? Well, regulation means controlling the rate of flow, the quantity of water flowing down the river. And as Celia pointed out, for the Dee, this is done by storing water up here at Lake Bala. Now, Lake Bala is large, but the water in it is conserved for recreational purposes, such as sailing or windsurfing. So, to maintain the level of the water in Lake Bala, an artificial reservoir was built here at Llyn Celyn. Llyn Celyn is used as a backup reservoir to the natural lake at Bala. It's carefully landscaped, blending man's intervention with the natural environment. The reservoir also generates hydroelectric power to supplement the national grid supply at times of peak demand. There's yet another reservoir, Llyn Brenig, on hand to back up the supply from Llyn Celyn if necessary. And these three reservoirs, one natural and two artificial, are at the disposal of the water engineers in regulating the Dee. Sluice gates are used to control the amount of water allowed from the reservoirs into the river. And it's how the engineer decides when to open or close these sluice gates that we're going to be looking at in this program. But what is the effect of a sudden release of water from the reservoir into the river? Well, we have to look downstream at the topography of the catchment area to see how the river runs. In the mountain areas, the river is narrow and runs rapidly because of the steep gradient. So any release from the lake will be quickly felt. Downstream, however, the river reaches a flat plain. It spreads out, and so it moves more slowly. That's why it takes 48 hours for any change at Bala to reach Chester. To keep track of what's happening over the whole catchment area on a day-to-day basis, monitoring stations have been built along the river at various points, and these record the river flow. These flow rate measurements keep a check on the amount of water flowing into the river from rainfall in the various parts of the catchment and the amount of water taken out of the river for domestic water supply or industrial use. In fact, in this stretch near Chester, most of the abstractions take place. For example, in this section between Farndon and Chester, up to 9 cubic meters of water are taken out every second. That's 750,000 cubic meters every day. So it's important to know that there'll be enough water left over by the time the river gets to Chester. This is the weir at Chester. It's very old and was built on a natural rock formation. The weir is a barrier, stopping seawater from getting any further upstream. To do this, the flow over the weir has to be at least 4 cubic meters per second. What river regulation means then is careful monitoring and decision-making about the amount of water to let out of the reservoirs. And to do this, we have to understand the natural behavior of the catchment area by taking measurements of rainfall and river flow at different points. And it's the numbers that we get from these measurements that characterize this particular catchment area. And we'll be looking at that later in the program. And all these measurements are relayed back here to the Welsh Water Authority station at Bala. Here, at the Bala control room, a computer stores data on river flow rates, reservoir levels and rainfall. This is updated every 30 minutes with measurements from the gauging stations along the Dee. Danny Roberts, the chief engineer, has a total picture of the state of the river. Given all this information coming in, how do you make the day-to-day decisions about managing and regulating the river?
It depends basically on what time of the year we're in and also the situation we're in at any given time. In the winter months, we're obviously more concerned with flood alleviation, and in the summer months, we're more concerned with river regulation. The assessment that we make each morning is for river regulation is whether or not the level down the Dee towards Farndon is at the point which we require to enable the various abstractors to take the abstracted quantity of water, still retaining a sufficient flow over Chester Weir, which is laid down under an Act of Parliament.
This is a legal limit.
It's a legal limit which we have got to maintain over the weir, and this was established in 1956 on the completion of the original Bala Lake scheme.
So what are you actually looking at in particular when you're doing making the decision about regulation?
Well, any time, the first and most important level is the one in Bala Lake itself, or Llyn Tegid. That is the governing level both for flood alleviation and, to a certain extent, to river regulation. In a natural lake, such as Bala, and which is controlled by a set of sluice gates, it's impossible to maintain a constant level. We have to maintain sufficient storage of water in the lake to permit a heavy belt of rain to be absorbed into the lake without causing any problems.
The accurate measurement of river flow rate is one of the crucial factors in this monitoring scheme. And it relies on a basic principle of hydraulics. And that is that the speed of flow of a river is dependent on the level of the water surface. So that if the flow speed changes for any reason, then there must be an accompanying change in the water level. Now there's a practical consequence to this principle, and that is in the calculation of river flow rate. You can put an obstruction into the river like this weir. And if you measure the level of the water over the weir, then that will adjust itself to the flow speed. And if you know what the dimensions of the weir are, you can then calculate the flow rate of the river. In order to relate river flow rate to the weir depth, the weir is first calibrated by taking measurements of water speed. The speed of the propeller registers the speed of the water. Now, the level of the water is measured by making a connection, a pipe connection, between a point on the weir itself and a gauging station up above. The water level is measured by a float in this well. Well, the position of that float is recorded continuously on this drum chart. And the result is the river hydrograph, which plots the level of the water above the weir, in other words, the river flow rate, against time. Now, the river hydrograph is perhaps the most valuable piece of information that we can get about the behavior of the river. Not only does it show us peak and minimum flows, but it also tells us a lot about the natural properties of the local catchment area. Now, we're going to be looking at this river hydrograph in more detail later in the programme. But there's one other vital piece of information that we need to go with this, and that's rainfall measurement. You'll be familiar with rainfall measurements from your work with the home experiment kit rainfall gauge. This one next to it is a standard Met Office rain gauge. It has standard dimensions, 5 inches diameter, 127 millimeters, and it stands 12 inches or 305 millimeters above level ground. Now, the conventional practice is to take a reading of the rainfall once every 24 hours. Usually at a fixed hour in the morning and officially at 9 a.m. Greenwich Mean Time. And this will give you a once daily record of the rainfall. However, if you were wanting to get the rainfall over a continuous period, in other words, to measure it continuously, you'd have to go to another type of device. And here at this gauging station, such a device exists. Basically, it's a large funnel which collects the rainfall and directs it down to the center. And underneath this funnel is a mechanism known as a tipping bucket mechanism. And every time the equivalent of 0.2 of a millimeter of rainfall falls into one of these little buckets, the bucket tips, and that event is recorded automatically. In this way, we can get a continuous record of the rainfall over a long period of time. So, here at the Bala Sluices gauging station, we're measuring two of the key variables, rainfall and river flow rate. And these readings are monitored continuously and automatically and are fed directly back to a central control room by telemetry.
So what are we going to do with all these measurements? Well, the answer lies here at these sluice gates, because these are the gates which are controlling the flow of the water out of the lake. And the engineers want to know when to raise and when to lower them. A wrong decision here could mean that water is wasted, which might be needed later on, or if too much is kept back, it could cause very serious flooding problems, costing many thousands of pounds. And to help us make these decisions, the computer is a very useful tool, because not only can it tell us how the river is behaving at the moment, it can also predict the levels downstream at Chester as a result of actions taken here at the sluice gates up to 2 days beforehand. The question is, how much water to release? When should these gates be opened? Too little water and the flow over Chester Weir will be too low. Too much water and the lake may drop to an unacceptable level. This can happen in a drought situation. And we then have to fall back on the reservoir at Lyn releasing water from the sluice gates here. These are the operational decisions at the heart of the River Dee regulation scheme.
To help us make those decisions, we need to be able to forecast the future behaviour of the river. Now, river flow rate depends on rainfall, and the relationship between rainfall and river flow rate is determined by the nature of the catchment area. Now, imagine the amount of water falling as rain over this whole catchment area, and all that water must end up in the river. The question is how long it takes for the rain to get to the river. This simple model gives you some idea of what's happening. Rain falling on the catchment infiltrates the soil. And in exceptional circumstances, it'll run straight off the surface. Eventually, however, all the water must finally get to the river. But the effect is that there is a delay or a lag period between the rain falling and the build-up of flow in the river. And when the rain stops, the river continues to flow, replenished by all the stored water in the subsoil of the catchment. Of course, with no rain at all, eventually the river flow must decrease over a period of time. And this is called the recessive flow of the river. There are other circumstances to take note of as well. For example, in the winter, when the soil moisture is fully saturated and all this storage capacity is used up, then most of the rain falling will just run directly off the surface. On the other hand, in the summer, when there may be a large deficit of soil moisture, then any rainfall there is will go in filling up the storage capacity. And it's these kind of conditions, low flow conditions, that Celia was talking about, where they'd have to open those sluice gates. All these features are evident from looking at the river hydrograph, the plot of river flow rate against time. Now, you remember the hydrograph I was looking at earlier at the gauging station. It's been replotted together with rainfall data for the period 30th of August to 7th of September 1983. And you can see the effect of rainfall on the river flow rate. Here's a particularly heavy bout of rain which started in the morning of the 2nd of September, building up to a peak of about 17 millimetres of rain over the 4-hour period around midnight. The effect on the river was dramatic. The river flow rose by over 300 times its low flow condition, and all in the space of 12 hours. Notice this short lag period between the maximum rainfall around midnight and the maximum river flow around 4 a.m. After the rain stops, the hydrograph shows this falling river flow, the recessive flow, steep at first and then gradually dying away over a period of days. Now, the shape of this curve is like a fingerprint for this part of the catchment. Every catchment area has its own fingerprint, its own characteristic. And it's this information about the natural characteristics of a catchment that is stored in the computer at Bala. And what the computer is doing is remembering these shapes for every part of the catchment, so that when new information comes in, the computer model can predict 2, 3, or 4 days in advance how the river is likely to behave. It's a useful management tool. Back in Bala, I asked Danny Roberts how he used these predictions to plan how much water to let out of the reservoirs.
Right, well, we know the quantity of water which the abstractors are taking, or which they are licensed to take. We know the flow which is required over Chester Weir. Therefore, we only have to estimate the actual recessive flows in the tributaries of the Dee. This we can do by utilization of the model, which enables us to determine exactly, or within 10%, of what the recessive flow in the Dee will be.
Well, what happens under extreme conditions? For example, when there's been no rain for about 2 or 3 weeks, a drought condition, what sort of actions would you be taking?
We would limit the discharge from Llyn in order to preserve water in the reservoir. And we'd limit this by increasing the discharge from the Brenig Reservoir, increasing it to, say, 4 cumecs, and reducing the flow from Llyn by that 4 cumecs, while still maintaining the flow in the Dee.
After passing through fields, farms and industry, the river reaches Chester Waterworks. Here, water is drawn through coarse screens and suspended solids are removed by air flotation and by filtration through sand beds. Finally, it is chlorinated before distribution to the population of Chester.
So, drawing off a glass of water to drink, in itself a very simple operation, depends on many complex operational decisions. The scheme we've been looking at here depends on a detailed understanding of how a natural river basin operates. The routine measurements which have been made over many years of rainfall, river flow levels, lake levels, sewage outfalls, river abstractions for drinking water, have all contributed to the mathematical modelling of the natural dynamic system. And so we're able to manage the River Dee in such a way that it remains a most attractive river, able to satisfy all the demands made on it and seldom getting out of control. And it is, of course, for this reason that river regulation schemes are so attractive and important from both an environmental and an engineering point of view.
In 5